Ready when you are.
Ready, Dan?
Ready.
Okay. So this is the class on electromagnetic induction and Lenz's law, Faraday's law, and this is how basically the guts of how generators and motors work, as well as a little bit on magnets. So how to describe, you get an EMF, an electromagnetic force, electromotive force, by moving a conductor in a magnetic field. That's pretty straightforward. And be able to derive the equation for that, that's also very straightforward. Magnetic flux and magnetic linkage, this stuff is kind of difficult conceptually. I made a model or two that might help get that point across. This, I think, is probably the most difficult thing to understand. Not compared to quantum physics, but compared to normal physics. And how you get an induced EMF by a time-changing magnetic field. That was one of Faraday's big contributions. And in fact, that's Faraday's law. And then we'll talk about Lenz's law. And I have a couple puzzles for you. Actually, one puzzle, and I guess two puzzles. One of which involves a railgun. So you need to know how to get a magnetic field from a current. And you always think of your right hand. Right hand rule. Sorry about that for lefties. So if you have a current, and let's say that you had a conductor, like a wire or something like that, and the current, the conventional current, goes this way, you can say that the magnetic field will go up in like a curve. It goes around, if the current is going this way, it goes around this way. Does that make sense? Guys, remember that from like last year? Okay. If you have, I'm trying to show this three-dimensionally that it's going around. Also, if you have a current loop, you can say if my current is going around in a loop, well, I can use my right hand and say, well, it looks like the current, the magnetic field, is going to curve up here through the middle. So, and go down on the outside. So that's how the magnetic field arises from currents. Now, when a charged particle is in a magnetic field and it's moving, it feels a force. And then again, we use the right-hand rule. And we typically use X's to denote a field that's going into the plane. That's kind of like an arrow. We're looking at the tail end of an arrow going in. And we use dots to indicate a field that's coming out of the plane. It's like an arrow heading towards you. So you might get scared of the arrows, but that's the idea. So here, if we have a magnetic field, so it's going into the board. If this is a positive particle, we use the right-hand rule. The thumb in the direction of motion of the particle, and the palm in the direction of the force it pushes. So this would be pushing up. And here, if it was going out of the plane, so the fingers in the direction of the field, the thumb in the direction of the velocity, that would be pushing down. So the particle here would get a force pushing down. And if it's a negative particle, it's just reversed. So here are just some examples of a charged particle moving in a magnetic field. So just to make sure that you guys are all with me, how about this one? What's the direction of the force? The velocity of this particle is going up. So what would be the direction of the force? I see people pointing to the right, so the field is coming from us, it's moving up, and it's going definitely to your right. Okay, good. Okay, and that is the main part of this. So if this was a conductor, say, and it's moving up, then the charged particles, well, let's say the positive particles, would then feel a force on this to move to the right. And so what would happen, and the negative particles would feel a force going to the left. And so what would happen here is that you build up a positive charge here and a negative charge here. If this was like a conductor moving in this direction. Does that make sense? So the charged particles inside the conductor will actually feel a force. And so let's say here's an example. So here we have field that's going into the board, it's going down, it's going to feel a force to the right, similar to what we were just doing. So we're going to get like excess positive charges here and excess negative charges here. And the force that each charge feels is like the charge on an electron or a proton times the velocity that the conductor is moving times the strength of the field. And so that's the force that the particles here are going to feel moving to the right. And they'll continue moving to the right until, let's say you have a positive particle here, and it's getting pushed over here by the magnetic field, but then you build up positive charges here, and those will repel positive charges. So there's going to be like an equilibrium condition here. And that's going to exist until, or that the magnetic field is going to be exactly equal to the electric field. And so this tells us, we can sort of divide through by the charge, and an electric field is measured in newtons per coulomb. We can also measure it in volts per meter. So if you consider this conductor to have a certain length, this is a length, that the voltage difference between the positive side and the negative side will be what we call an electromotive force, and it's just equal to E, which will be QdV times the length here. Well, I guess we divided through by the charge. So it's basically VB times the length. And so this lets us calculate what the charge, what the voltage will be from like one side of a conductor to another side of the conductor, just by moving it through a magnetic field. Make sense? And this is actually how you get a generator, essentially. You take a piece of conductor, move it through a magnetic field, and you build up a voltage. And yeah, that's how generators work. And this would be, and the magnetic field we measure in Tesla, and you might remember the joke about my wife's name, or Webers per meter squared. And a Weber per meter squared, what the hell is that? Well, Weber per meter squared is a Tesla. And Webers are kind of like a unit of magnetic flux. And let's see. So I'm not sure that we have time to go through this, but if we wanted to, we could say, well, what would be the induced EMF on a wire if its length were 0.42 meters, if it was moving at 25 meters per second, and it was going through a perpendicular magnetic field of 0.38 Tesla. So if we multiply 0.38 Tesla by 0.42 meters and times 25 meters per second, those should all multiply out to be something like 3.99 volts. So that would be a field that you might see inside close to maybe an NMR machine, fairly high field. And if you wanted to get this to be like 86 volts, you need to like moving at 539 meters per second, so close to twice the speed of sound. But you can do those types of calculations. And I think I give examples in the worksheets. Now, Faraday was very, probably the best experimental physicist maybe ever, was trying to figure out how you get an electric current by a magnetic field. And he figured out that it wasn't just the magnetic field, but something had to be changing. And he basically said he had a very good feel for these lines of magnetic force. And he called it the magnetic flux. And what he said is that the current in a loop is basically proportional to the change in the number of field lines, the number of flux lines going through that loop. And I have some visual props here.